that is where the model is, and I've also started recording, so let's wait for Revit to open. As it opens, I'll open my paint. Now, column design. Column design is very simple for the manual design. Even using the software, it's also very simple, because the function of the column is just to carry loads. It does not perform any other work. It's just to carry loads. But when it comes to slabs, you have to first of all decompose the loads, calculate the loads that that are coming to the slab, especially the live load, the dead loads. So all those loads, you have to put them on slab. So slab will suffer a lot, but the good news is that they will decompose these loads and transmit them to the beams. Now beams will also suffer. Why? Because it's receiving loads from the slab, a lot of loads, area loads, which is converted to UDL. I think we did that, and you understand the process. And then after that, these loads will be transferred to beams. It's also getting loads from the walls, because on top of the beam, if you'll just allow me to draw this. So this one is actually a section view. We are viewing this building from one side. It's like a 3D building, but we are just viewing the elevation like this. Then this one is then this one is another floor like this. Maybe we can just assume here is the ground level, and this is the foundation actually. Now, so I'm going to assume this, that this is the plan that I have created like this. So when you look at this building from bottom, we will actually see this column. We will see another column here, then we will see another column here. So we'll see 3 columns, and these are the columns that I'm talking about. And this building will go in that direction like that, so that we have another columns like these ones like that. So for us to design these columns, I have presented 3 columns, but I'll want to present more columns like this one, and this one. So here I have presented 6 columns actually, and I'm going to discuss different types of columns and how to design them. So here we are having types of columns. So types of columns, we have 3 of them. We have 3 types of columns. We have a corner column, this corner column, which only supports 2 beams. So this one is corner column. Number 2, we have a perimeter column. Perimeter column is the column that supports more than 2 beams, but it's at the edge of the building. So like this one, it's an edge column or a perimeter column. So this one will be C2. We'll just name it, abbreviate it by C2. Then we have internal columns, which supports beams from all the sides, and this one I'll just name it C3 as an internal column like this. Now designing these columns, it's not so difficult. It's very easy actually. In manual design, we use area method, tributary area method. So for this one, we will just divide the beams that are being supported by this column into a half. So I'll just come here and take a half the beam will be supported by this column, and a half the beam will be supported by this other column like that. Then also this one I'll divide it by a half like this. So this one will yield us an area that this column is going to support. So this area is actually the slab area, this area. So we have to calculate this area. Then after getting this area, we convert the slab load. Remember, slab load will be given in kilonewtons per meter squared. So you have to convert this kilonewton per meter squared into kilonewtons. So the best way to do this, you just multiply it by the area, and this area is this tributary area from the slab. And to get this tributary area method, you just use the supporting elements, that is the beams, and you divide them into half, and that will be okay with you. When it comes to this perimeter column, it's the same procedure. You just divide this beam into half. We've already done so, like this. So a half. Then we divide this one also into half. Then we divide also this one into half. So you can divide first, then you just link your divisions like this. Then this means this column is going to support this amount of area. So if you have this one as 4 meters, this will mean this one is 2 meters. And if we have this one as 5 meters, this will mean this one is 2.5. So you just calculate the area, and let's assume this one is let's assume this one is 4.4. Let me just put the dimensions right now. So I'll put the dimension using this blue. So if we assume I will use another color, maybe let me add a different color, magenta. So if we assume this one is 4.4 and this one is 5.6 and this one is 4 and this one is 3.8, then it's going to be very simple. It's going to be very simple. So for us to simplify this process, it's very easy. So this one, it will be 2 meters. So this means if we divide this beam into 2, then we will get 2 meters here. Then if we divide this beam into 2, we will get 2.8. So this length is actually 2.8, and this one, and this length, this other length is 2.2 because we are just dividing this by 2 like this. So this one is 2.2, this one is 2.2, and this one is 2 like this. So the total length from here to here will actually be sum of this, which is actually, this one is 5 meters. So to get this area that this column is supporting is very simple now. We just take 5 meters times 2 meters, then we will get 10 meters. So this one is supporting 10 meter squared. Then internal column, it's also very simple actually. It's also simple. We just continue like this. Now we divide this beam into 2. We get this portion going to the column. Also this portion will take its all to the column. Then when it comes to this one, we divide it by 2. So this one is a half, this beam like this. So this all area is being supported by the internal column like this. So we will get the area of C3. The area of C3 will actually be 5, the total length, then plus, times this length. So to get this, it's very simple. This one is 2 and this one is 1.9. If you can do your mathematics, then you'll get this. So when you add this, you'll get 3.9. When you add this, you'll get 3.9. If I go wrong, please you unmute and correct me very fast. So 3.9 times 5, you'll get 19.5 meter squared. So this 19.5 meters squared is the area that this column is going to support. And the area that this column is supporting, the C2, is actually 5 multiplied by 2, which is 10. Then, when it comes to the C1, the corner columns are always very small. The reason is very simple, because they support little load. So to get the load that this column is supporting, you just take the area, you just take the length 2.2, then the height 2, or the width 2, then this one you'll get 4.4 meter squared like this. So I am going to pause and ask you a question if we are together. Then if you confirm that we are together, then we can continue. Perfect. So that is how we calculate the area that these items are going to support. Now let's come to C1. I want us to design C1 first. So C1, we have to calculate the loads from the slab. And loads from the slab, it's very simple. We just need we will start with live load. I'm going to assume that this structure of ours is a residential building that is going to support a live load of 3 kilonewton per meter squared. And superimposed dead load, I'll use 2.5 for this floor. Now, for the superimposed dead load, this one is actually loads of the partitions, live load, loads of the partitions, surfaces and finishes. This one will give us the superimposed dead load in kilonewton per meter squared. So this one is also very, very important. You should not take note of that. So how do we convert this live load into a point load that is going to be supported by the column? It's very simple also. You just take your load 3 kilonewton per meter squared, then you multiply by the area. So from this pressure, I think you remember we said pressure is equals to force all over, I think this one is physics form 2, all over area. So for you to get the axial force, for you to get the force, it's also simple. You just cross multiply and you'll get pressure, which is actually this load, multiplied by the area. And this one will give you the force in kilonewtons. This one will give you the force in kilonewtons. So I'll take the area, the load, which is 3, multiplied by 4.4. And this one will give me, I'll just continue. So if I take 3 multiplied by 4.4, then I'll get 13.2. Maybe you can also be doing from your end to confirm. So this one is 13.2 kilonewtons. Then I will just do 2 columns. Then from the 2 columns, I think you will understand. So let's do for C2 also here. Now for C2 live load, its live load will also be the same thing, 3 multiplied by the area. For C2 the area is 10, so this one will give us 30 kilonewtons. 30 kilonewtons. I'm writing using my mouse, so you should not worry about my handwriting. Then for C3 it is going, the live load is going to be 3, then multiply by the area, which is 19.5. 19.5. So when you do this, I'll just take 3 multiply by 19.5, then from my end I'm getting 58.5. This one is 58.5. Now one thing you should take note of is that this one is 30. This one is 30. I'll just erase and rewrite. I hope this one is the eraser. One thing you should take note of is that all these loads are actually all these loads, this one is 30, are actually unfactored loads. We've not put any factor of safety. So if you are doing with Eurocode or BS 110, it's upon you. This is the procedure. You'll only insert the factors of safety later. Now that is live load, all for the 3 columns. This one is giving us 58.5, this one is giving us 30, and this one is giving us 13.2. We will go to superimposed dead load. I'll just write it like this. So for superimposed dead load, I'll just write DL, but please remember, make sure you remember this. So it will be 2.5 multiplied by 4.4, and this one will get, I'll just be doing it very fast also. So 2.5 multiplied by 4.4, this one will be 11. Remember the units now in columns are in kilonewtons. It's actually axial load, so just remember the units are in kilonewton. Then this one will be 2.5 multiplied by 10. Then I'll get 25 kilonewtons. Then for C3 it will be 2.5 multiplied by 19.5. 19.5. So this one is giving me 48. This one is giving me 48.75. I'll just reduce the size like that. So it's actually 45.7. 48.75 like that. Now, after calculating the live load and the superimposed dead load, these ones are area loads. Sorry, these ones are area loads from the slab. Now, the next thing is to calculate loads from the beams. Let me just write this one well, so that maybe you take note that this one is the slab. So I'll pick this, then I'll make sure this one is picked. So this one is load from the slab. Sorry for the handwriting. Now we will go to the beams. To the beams, loads from the beams, it's simple. It's very simple. It's very simple. So how do we calculate these loads from the beams? This is how we do it. First of all, you have to get you have to get the length of the beam that this column is supporting. And to get the length of the beam that this column is supporting, it's also very simple. You just take sum of this beam plus this beam, unless these beams are of different size. But here we are just going to assume a typical beam of size 200 by 450. So we are going to assume beams. Something that we are forgetting. Sorry for this. We've not finished the slab. We also have to calculate this one is superimposed dead load, but we have to calculate. Okay, let me just add here superimposed dead load, superimposed dead load, then superimposed dead load. That's okay. Now we also have to calculate now the dead load from the slab or the self weight. Let me just put here self weight. I forgot to tell you this. Now for us to get the self weight, we must know the thickness of the slab. So slab we will assume 150. Now for this 150, you have to get the self weight. To get the self weight is very simple. You just take the depth of the slab or the thickness of the slab, then you multiply it by the density of concrete. So if we assume that density of concrete for all the elements is 24, we'll assume 24 for now. So if you take 24 multiplied by 0.150, then you'll get 3.6. And this 3.6 is actually area load. So this one is in kilonewton per meter squared, like this. So take note of this, please. I forgot to tell you this. Now after you've calculated that one, so this one, it will just be equal to 3.6. so I'll just do this. The slab, for the slab load, I'll just calculate it here, but okay, let me just do it here, but you have to remember here. So it is 3.6 multiplied by the area, which is 4.4. If you do this, 3.6 times 4.4, from my calculator I'm getting 15.84. Then here self weight, I'll get 3.6 times 10. 3.6 times 10, I'll get 36. Then lastly, I'll get 3.6. This one is superimposed dead load, and this one is self weight. So this one is 3.6 times 19.5. So if I do this 19.5, then I'm getting 70.2. 70.2, like this. After calculating the loads from the slab, then you have to calculate loads from these other elements. Just a minute, engineer, please. I think we will continue. So here we've calculated the slab load, and I think you've seen how to calculate that. So in any beam, as much as you are doing the manual design, then you should just remember this is how we approach the transfer of loads from the slab to the columns. I know we have to pass these slabs to the beams, then beams to the columns. Then that one is not manual way, because that one will now be, it's like you are doing the finite element analysis method where there is a clear flow of loads from one element to another. But here, that is how we calculate the loads. Now, when it comes to beams, we will, as I was saying, you must have the dimensions of the beam. Now, for the beams here, we are going to assume beams. We are going to assume 200 by 450. So 200 by 450. Sorry, by 450. Now, what does this one mean? Remember, this 450 is actually the depth, the total height. Assuming that this one is your slab, I'll just draw it here very fast. If we assume that this thickness is 150 that we are saying, right now we will keep the columns as line loads, because as line elements, because we don't know the thickness of the columns. We'll just keep them as lines. So this one is the slab, 150 millimeter thickness. Now when it comes to beams, it is 450. This 450, it is from the top here to where it is ending, up to somewhere here. So this is the total thickness of the beam. 450 is actually from here up to here. So what is my point here? If this is the total depth of the beam, and we want to calculate the load that is being transferred from the beam to the column, then we are not supposed to take the total depth. Why? Because some depth is already taken by the column, by the slab. So this 150, yes, we have to remove this 150, so that when we calculate the loads due to beams, we just have to take 0.2 multiplied by the 300. So you take 450 minus 150, you'll get 300, so it will be 0.3. Then you multiply by the density. Remember, density is in kilonewtons per meter cubic. So that cubic, when you multiply it by this meter, this is meter squared, then assuming that this one is 24, then you will get a load of the beam in UDL format, that is per meter. So it will be 0.2 multiplied by 0.3 times 24, then you will get 1.44. 1.44. But remember, this one was area, but this one is in kilonewton per meter. So, but remember, columns are expecting this load not to be in UDL format. Columns are expecting this load to be in kilonewton or in a point format. So how do we convert this load from this UDL format line load, we call them line load or element load, into a point load to the column? It's very simple. You just multiply this by the meter. So which meter are we talking about? So here it will be, so this beam load is actually dead load. It will be 1.44 for all the beams. Of course, I'm assuming that all beams are 450. So I'll multiply this by the length of the beam. And the length of the beam in this case, it is this length 2 and this length 2.2, the total length that this beam is supporting. So when you add this 2 plus 2.2, you must get 4.2. So I'll just multiply by 4.2 as the length here. So when you do this, then it will be very simple. You just multiply by 4.2, and here I'll get 6.048. Then the same thing here. I'll just come to the beam dead load here. I'll take it as 1.44, the same UDL, multiply by the length. So the only thing that is changing here is actually the length that this C2 is supporting, the length of the beam that this C2 is supporting. And when you look at this, in essence, it's actually this total length, because it's supporting a half, which is 2.2, plus this a half, which is 2.8, a total of 5, then plus this a half, which is 2. So when you add this length together, you must get 7. So this one is 7. So I'll just take 1.44 then multiply by 7, and this one will give me 10.08. Then we will continue to dead load for C3. Now, dead load for C3 from the beam, it will also be 1.44. Then you multiply this by the total length that this beam is supporting. And this one is more than symbol. You just take this total length from here up to here, which is 5. Then plus this total length, which is 2 plus 1.9. So it will be 5 plus this one is 3.9. So when you take 5 plus 3.9, you get 8.9. You get 8, sorry. You get 8.9 here. So I'll just do this. Now this 8.9, you multiply it by the UDL that the beam is producing. Then here I'll get 12.16 like this. 12.16 like that. Now we are done with the beams. The next load is actually the columns, I mean the walls. So on top of this beam, we have, this is the wall. Maybe we have the windows here, maybe we have doors, something like this. But for design, we will just assume that this old beam is having a wall on top. This is the masonry wall, so we'll just assume that we have wall on top. Otherwise, you can also reduce the load that we are going to calculate, but for now we are just going to assume this beam is supporting a wall load on top of it. So how do we calculate wall load? It's also very simple. So wall load, it's also a line load or a UDL load, which will be in per meter format. So how do we do this? It's very simple. One, you have to know the thickness of the wall that is sitting on this beam. So the thickness for now we will assume 200, which is 0.2. Then we also have to know the height. That is very, very crucial. So to get the height of the beam that is sitting on this the height of the wall that is sitting on this beam, it is very simple. We will assume, I will use this height. Let me use this floor. So this one is 450. This one is 450, and this is the height of the wall sitting on this beam, assuming that this one is another floor, maybe first floor or so. And if we assume that the total height is 3 meters, or if this is what we have from the architectural plan, then it becomes more than easy or simple. You just take the difference between 3 and 450, then you will get the height of the wall. And for us to get this, if you take 3000 minus 450, you will get 2550. So that one will be, I'll just undo for this because I want to maintain the color. So this one will be 2.55. Now, when you multiply the length times length, then you will get length squares. So this means you will get the area. But we want to get this one into a load, kilonewton per meter. So to do so, you have to multiply this by the density of the wall. In essence, I always assume the density of the wall to be 18. But please go with what is supposed to be. But for now, we'll just assume 18. So when you take 0.2 times 2.55, then multiply by 18, you should get something like 9.18, and this one is kilonewton per meter like this. Now this load will be the load that will be applied to all the beams, will sit on all the beams. So here you have to calculate the load from the walls. So I'll just write here walls. Now for the walls, I'm using magenta. The walls is actually dead load like this. Now it's very simple also. It's also very simple. So how do we approach this? You take the load which is just the way we did for this one. We just take the load 9.18, then you multiply by the length of the beam. It's just the same thing, because if the wall is setting on this beam and we just want the load that will be supported by this column from the wall, then it is just a half the beam or a half the wall, because this is how it will be. A half will come to this column, then a half will come to this column. So we just take the length of the beams. So it will be multiplied by 4.2. So this one, if you do this, let me just do it very fast. So it will be 9.18 multiplied by 4.2. So this one I'll get 38.556. Then I'll just write dead load, but this is, we are using magenta for walls, you will understand. So for this one, it will be 9.18. Let me just write it, I wanted to skip. 9.18 multiplied by 7. I'll just keep the lengths. I think you understand it right now. So this one will be 64.26. Then lastly, the dead load for this one will be 9.18. And remember, this dead load I'm talking of, the dead load from the wall. Don't confuse from the other dead loads. Then multiply by, this one is 8.9, I think. 8.9. So 8.9, I'll get 81.702, like that. Now we will continue. We are remaining with one wall that is coming actually to our column. It's actually column self weight. So I'll just keep the black. So column self weight. For us to get the column self weight, it's not easy because we don't have the size of that column. So here, for small buildings, we always assume a symbol. We'll just start with a column of 200 by 200. So if you take a column of 200, this one is also dead load. And for columns, I'll just use maybe we can use this color, or let me use light green. This one. So this one is also dead load, and it's very simple. So it is 0.2 multiply, we will assume a square column of 0.2 by 0.2, then multiply by density. Density is actually 24. Then this one will give you load in per meter. The format will be per meter, but we want this load to be axial, so we will have to multiply it by the height of that column, and the column is actually running from here to here. So it's actually the height that we used here, which is 2.55. 2.55. So this one will give us, let me just do it. So 2.55 times 0.2 times 0.2, then times 24 times 24. I am getting 2.448. 2.448, like this, and this 2.448 will apply to all columns because we've assumed that all the size of the column is that. I'll unmute again and just confirm that we are together. Now I will just unzoom to have a small view, then I'll just increase the paper size. I'll unzoom again. Let me just unzoom it like this. I want us to have a very good working space. Now let us do this. I'll increase this size like this, then like this. So let us assume the following. We are going to assume that our building is like this. I'll just cut this section. Assuming that we are viewing this building from one side like this, Then we have one floor, second, third, then this one is actually the fourth. Then we assume we have our ground floor at this point, and the other one is actually the foundation. So this one is ground floor, then this one is first, this one is second, this one is third, and this one is roof floor. So here we just have to know the number of columns that we are having. So we have 1, 2, 3, 4, 5 columns. We have this one, we have this one, the columns that we are supposed to design, this one, and this one. So we have 5 columns actually. Now, how do we, I will start with, now we are going to focus on one column. Then from this one column, I think we will, you will now use the same knowledge to do the other columns. So how do we, now that we know very well we have 5 columns that we are supposed to design, how do we now accumulate these loads? The first thing is to calculate the total live load. The first thing is to calculate the total live load. Maybe I can just do this again, so I'll remove it. So I'll use red now to calculate the total live load that each column is supporting. So live load will just come here to slab, and as we can see, the total live load is 13.2. This one is 13.2 per floor. 13.2. So let's do it like this. Let's do it like this. Maybe we can just come up with something like a table, okay, like this. I don't know if I'm doing the right thing, but okay, I'll just be adding as we continue. So we will start with the column C1. Live load here is 13.2. So 13.2. This 13.2 is live load per floor. We'll just assume that, but you have to calculate live load for each floor based on the load that floor is supporting. But assuming that per floor this is the live load, then we will have 5 columns. We will have column 1 here, we will have column 2 here, we will have column 3 here, we will have column 4 here. Let me just remove this. 2, 3, 4, then 5, like that. Then here I will just use black. So I'll start with live load for this column C1. So for this column we have this one, maybe we can just use green. So this one we have 13.2, 13.2, then 13.2, 13.2. So let me show you something. Let me show you something first. When you look at this one, the slabs, this slab will bring its load to this column. This one will bring its load to here. So we have 1, 2, 3, 4, 5 slabs like that. So that's what I wanted to show you. And here we have 1, 2, 3, 4. So the last one will be here, 13.2, like that. So after getting this 13.2, then we are actually done. The next thing is to get all the dead loads per floor. So it's also very simple. We will just add this 11. So please, you can take your calculator. For me, I'm taking 11. I'll just type 11 plus another live load. Another dead load is this 15.84. Then beams, it is plus 6.048. Then plus walls, it is 38.565. 5, this one is, I don't know what is this, but I'll just assume that 38.56. I'll just assume that, hoping that it's correct. Then plus this one 2.448. So the total load here, the total dead load that we are getting here, let me type it here. I will tell you the reason. So it is 73.8 596. I'm typing it here because when you look at this floor, this load, this total load will actually affect this floor, but here we don't have the wall load. So I'll just, for the first floor, I'll just remove the wall load, which is 38. I'll just delete it from my calculator here. 3856, I'll just delete it. Then I'm getting 35. So this one is 35 because we don't have wall load on top there. Unless if you have parapet wall, then you can just include this wall load. But it's always good to do this in your in the Excel. Then here, so this, all this will be 73.856, 73.856, then 73.856. Now these ones are actually the dead loads. This one is live load and this one is dead load per floor. So we have to accumulate these loads for us to come up with something good. Before we accumulate these loads, so I'll start with the loads that we are going to use for foundation design. Remember, for foundation design, we just use unfactored load. We call them service loads. So we have to just add these two as they are like this. So we just have to add. But here, okay, I'll just add them. So if you add these two, I will add and accumulate them. Please take note of what I'm saying. So the first one is 13.2 plus 35.336. So this one will just remain as it is. So it will be 48.536, like this. So this load is actually the load on top of that slab. Then here I'll just write service load, serviceability. Then this one I'll just write ULS, ultimate limit state. So for the ultimate limit state, I'm going to assume we are going to use BSETA 110. So it will be in bracket 1.4 multiplied by dead load, which is this one, that 5.336. I'm assuming that. Then plus live load 1.6 multiplied by 13.2. So this one will give me 70.59, like this. Now these two loads are very, very important. This one for foundation design, this one for reinforcement design. So we will continue like this. I'll just let me continue like this first, but remember we have to accumulate them. So I'll just calculate and write them here, then we will continue. So 13.2 plus this one is 73.856. I'm getting 85.056. Then for the, this one is for the service. Then for the ultimate, so I'll incorporate 1.4 multiplied by, this one is 73.856, then plus 1.6 times, this one is 13.2. So I'm getting 124.518. So these are the two loads, serviceability and the ultimate for this floor. But each floor you have to accumulate because the column is now going to have cumulative loads. So how do we get the load for this one? Of course we will calculate it and have it like this, but you have to accumulate. So to get this one, I will take 48.536 plus what that floor is giving us, 85.056, maybe 056. So this one is I'm getting 133.59. I'll put it in two decimal places. Then to get this one, we'll have to add these loads, and which is this one. So I'll just add it again. I'll just say equals to, then plus this one is 85.056. So this one I'm getting 218.65. Then this one I'll just add the same load. This one, because if you do this, you'll just get the same load. I'm getting now plus 85.0056. Here I'm getting 3 or 3.704 like this. Then lastly I'll plus 85.056. I am getting 388 here. 388.76 like that. Then we do the same thing for this one. So I'll just take 70. I wanted this calculator to accumulate. I don't know what's the problem. Plus 56. So this one is 7059 plus 124.518. So I'm getting 195.11. Then I'll say plus 124 plus 124.518. I'm getting 319.62. Then here this one is 319. So after this we have to add the 124 again. I'm getting 444.14. Then I'm getting 568.65. Now after this, you now use this one is in kilonewton, so these are the loads that we are going to use. Now when you want to convert this load to the section of the column that you are supposed to design, it's very simple. There is a book I'll share with you. You just take this load, then this load is in kilonewtons, so we will assume a square footing for now. So if you want a square footing, then it's very simple. You just take this load 568.65, then you multiply it by 1000. You convert it to newtons. You'll get 568,650. Then this one you divide it by 50. So if you divide, you'll get the area of the column will be 11,373. So this one is for preliminary design. Then this area, you square root it if you want the square footing. So I'll just square root it. 11.
Why do we divide it by 50?
50 is for preliminary design. That is from the expert's point of view. If you divide by 50, you'll get the size of the column that will be suitable enough to carry your loads. So for preliminary design, you multiply by 1000, you convert it to newtons, then you divide by 50 to get the area of the column, bottom column that will be able to support all these loads. So you divide by 50, then you'll get 106. So 106, this one is too small. You'll just assume a column of 200 by 200. Up to there, do you have any question? Engineer, let me open the Excel sheet. Maybe we can simplify all these calculations. So yeah, this one. So here we've assumed that we have 5 columns like this, and the floor of each column is actually, this one is 5, yes, it's 150. Then superimposed dead load, we've assumed a superimposed dead load of what was it, of 2.5 and live load of 3 per floor. So I'll just put 2.5, then live load 3, floor 3000, then 450 by 200, then the wall thickness we've said is 200. Now here I said we assume 200 by 200 column. Here just assume 200 by 200 column. Then you have to know the distance in X that this column is supporting. So as we can see from here, it is supporting a distance of 4 meters. The total distance in x is actually from here to another column is 4.4. So it is 4400. I'll just enter 4400 here. Then in y, it is where we have 4000. If you saw that from this, it is 4000. So the software will just calculate for us the 2 and that. So as you can see from our calculations or from our discussions, we've said if we do this, then we'll get the following. Service load will be 87. The first one will give us 87.1. So this 87.1, maybe I can just look at it keenly. This one is okay. Yes. Oh yes, we don't have wall load, but anyways, for now we'll just assume. So we will get that. Then this other floors will get this service load, but uncumulative. Also the ultimate, I think the ultimate we've calculated it here. It's 124.516. So this one is giving us this one like this. Let me check something. Okay, yes, I think it's fine. Now after this, you cumulate your load. So as you can see, cumulatively we will have the first one. This one was 48. I'm trying to get the reason why this one is giving us this. So you cumulate your loads keenly as we've done them. Then you also cumulate the ultimate. So the ultimate load here is 610. Let me look at why this one is 35 and why this one is 24. I'll just take a look very fast. Okay, so this floor, we can put here 0 like that. Yes, that one is okay because we don't want the wall load here. The first floor actually we don't have it like that. So after this you do your sizing. As I said, the sizing you can assume one size as 200. Then this other one will just come. Otherwise, if you want to do a square, you just square root. So here we are getting 200 by 136, which does not make sense. So we'll just go with a column of 200 by 200. So with this column of 200 by 200, then it is now easier for us to start now putting our reinforcement or to start doing the design. So for us to do the design, it's also very simple. We will go to clause 3.8 of BSETA 110 if you are using BSETA 110, or to Eurocode. Okay, let me just pause. Let me just clarify something here. X distance is actually the distance from this column when we are using Excel. Is the distance from this column to any nearby column in X direction. So if we go to X direction, maybe I can just use magenta. From this column we are going to X direction. So to this direction we are meeting this column. So this means these two columns will share the loads in that portion in X direction. So that's why we are putting 44 here. In Y direction, it is the distance from here upwards or downwards to this column. So let me use this internal column, maybe you will understand. In X direction from this column is supporting this beam in X direction, X positive and X negative. So towards negative direction, but in X direction, it's actually meeting this column. So we terminate it here, and here we terminate it here. So we take this whole distance. So when you sum up this distance, it will actually be 10,000. So here you put 10,000 in X direction because they are sharing. It will just calculate itself, but manually I have shown you how to do so. Then in Y direction, we go up to where we are going to meet another column, probably here, then down to where we are going to meet another column, probably here. So the total distance, this one, is what we record, which is 7.8, and in mathematics we call it 7800, like that. So in that internal column, if we are dealing with that internal column like this, then this is the load that we are getting. This is the load that you are getting. So that internal column will actually...
No, we are, just,
Okay. Yeah, sorry. This one should be 10,000. Sorry for this. Yeah, so this internal column will actually be 200 by 482, which is actually 200 by 500. So before you go to design in the Excel, you make sure you do your design like this. So it will be 200 by 500, and as you can see, it is still passing. If it goes beyond 500, then you cannot use that section like this. So this is how we do the sizing of the column. So in the next session, we'll discuss the design of the column.